Today we're going to start a new chapter on exponents, and we are going to do a lot of review today on some laws of exponents that you've learned before in Algebra 2. We're just going to review them and make sure we're all in the same place as to understanding how to use these exponent laws before we dive deeper into exponents and using exponents to model certain things, before we dive into logarithms, all of that. So here's just a couple of examples. So here's the first one, square root of 8 times square root of 12. Now you are allowed, absolutely allowed, to multiply things that are under the same root. So since these are both square roots, we can multiply them both as long as we put them both under a square root. So this is equal to the square root of 96. Now when we want to simplify a radical as much as possible, we want to see if there are any factors of the number under the radical that are perfect squares. So in other words, do we have 4 or 9 or 16 or 25 or any of those factors of the number underneath the square root? In this case, 16 is a factor of 96. You want to try to find the largest perfect square that you can take out. So we can rewrite 96 as 16 times 6. And the square root of 16, because it is a perfect square, it comes out to be exactly 4. So we can simplify that, and then this becomes 4 root 6. All right, let's look at the next one, square root of 12 minus square root of 75. Now when it comes to subtracting or adding radicals, you're not going to be able to do so unless you have the same exact thing under the square root. What we can do though here is we can simplify each of these. So see if we can simplify the square root of 12, do the same thing as we did with the square root of 96. See if there are any factors of 12 that are perfect squares. Seems like 4 would be the answer there. And for 75, 25 is a perfect square. That's a factor of 75. So we can rewrite these as 4 times 3 and 25 times 3. Now we'll go ahead and simplify it by taking the square root of the perfect square. So this becomes 2 root 3, and the second one becomes 5 root 3. Now actually, you'll notice that for both of these, we have the same number under the square root. We have a 3 under the square root. That means I can now combine these two. Now when you combine these two, you're only going to be subtracting the number that's in front. So we have 2 root 3 minus 5 root 3. That means now we have negative 3 root 3. You can think of this as the same as when you have 2x minus 5x, right? The x's don't change, but 2 minus 5 is negative 3. So 2x minus 5x is negative 3x. In the same way, 2 root 3 minus 5 root 3 is going to equal negative 3 root 3. All right, next one. This one is a cube root. Okay, with a cube root, remember that now instead of looking at perfect squares, right, square roots, you're looking for perfect squares. Cube root, you're trying to see if there are any perfect cubes. So what are perfect cubes? So 1 to the third is 1, 2 to the third is 8, 3 to the third is 27, 4 to the third is 64, and so on and so on. So what I'm going to do here to simplify this is I'm going to break this down into each of its parts. So I'm going to write this as the cube root of 8 times the cube root of x to the 6th times the cube root of y to the 4th. Okay, the cube root of 8 is 2. Now, for the x to the 6th, you can think of this as, well, I can break this down into perfect cubes. So if we broke this down into perfect cubes, I would have x cubed times x cubed. And then we can do the same thing here with y to the 4th. We can write it as y cubed times y. Right, so I'm trying to write out factors that are perfect cubes. Cube root of 8 happens to be a perfect cube in and of itself, so we could just have simplified that. And x to the third times x to the third is x to the 6th. And it just so happens that it breaks down into exactly 2 x cubes two perfect cubes. And then for the y to the fourth, we only have y cubed, that's a perfect cube, and then we still have a y left. Okay, so now if you take the cube root of each of these, so the cube root of x cubed is just x. We have to do that a second time, so the cube root of x cubed is x. So now we have two x's, so we have 2x squared. And then the cube root of y cubed is y. And then the one that's still under the cube root, we have to keep under the cube root. Okay, the last one in this set of examples, we have 5 plus the square root of c times 5 minus the square root of c. So when you're dealing with radicals and you have to distribute, we can just multiply just like we were doing before. And then once we've multiplied, we can see if there are things that might cancel out that are like terms that we can combine. So 5 times 5, that's 25. 5 times negative root c, so minus 5 root c, and then plus 5 root c, and then minus root c squared. Now what's nice here is you'll notice we have a minus 5 root c and a plus 5 root c. Those are going to cancel. And then the root c squared, once you square it, the squared and the square root cancel each other out, so you're left with just minus c. So this is equal to 25 minus c, and that's as simplified as you can make that. Okay, let's talk about nth roots. So we've looked at square roots, we've looked at cube roots, but you could actually have any number there. It doesn't have to be just a square root, it doesn't just have to be a cube root. It could be any number n. So let's say we let c be a real number and n is a positive integer. Then the nth root of c you can write as one of the following, either as literally n with the root c, and then the other way to write it without a radical is to write it as what we call a rational exponent. So c to the 1 over n. So you have a fraction in the exponent. We call that a rational exponent. Rational meaning it's a type of exponent that can be expressed as a ratio, right? A rational exponent. Okay, let's kind of get used to seeing things written with rational exponents, and we can translate them into radicals if we need to, if that's helpful. So the first one here, 16 to the 1/2, we could write that as the square root of 16. Now, normally with roots, you normally would write the little number, but with square roots, the 2 is implied. Anytime there is no number on the radical, then you know it's a square root. If there is a number, then you know it's that nth root. Okay, so square root of 16, that's equal to 4. So 16 to the 1/2 is equal to 4. All right, 8 to the 2/3. Now what do you do with the 2? The 2 stays there, but the 3 will be used in the radical. So this is the cube root of 8 squared. Okay, so it's just the denominator that moves. You can think of it as looking at 16 to the 1/2 as the square root of 16 to the first power. Obviously, anything to the first power is just itself, so it doesn't affect our answer there. But here, cube root of 8 squared. Okay, so the cube root of 8 is 2, so 2 squared is 4. Now, does it matter whether you square it first and then take the cube root, or if you take the cube root first and then square it? No, it doesn't. It actually doesn't matter. So if you actually squared the 8 first, then you'd have the cube root of 64, and the cube root of 64 is in fact 4. Okay, next one, 16 to the 3/4 power. So we'll rewrite that as the 4th root of 16 cubed. The 4th root of 16 is 2. 2 to the 3rd is 8. Okay, the last one here, we have the entire thing, 27x cubed, all raised to the 1/3 power. So I'm going to write this entire thing under a cube root. Now the cube root of 27, and it's a perfect cube, so that's going to be 3. And then the cube root of x cubed, that's going to be x. So this is equal to 3x. Okay, let's go over a couple of laws of exponents. So here's the first law of exponents. If you have the same base, c, raised to the r power, times c to the s power, that's the same as c raised to the r plus s power. So in other words, you can add the exponents together if you have the same base and you're multiplying those two together. Similarly, if you're dividing things with the same base, you can subtract the exponent. So c to the r over c to the s is equal to c to the r minus s. The third law of exponents is if you have a power raised to a power, so if you have c to the r that's raised to the s, then you can multiply those exponents. So notice what we've been doing so far with the exponents. In the first one, we added those exponents when we were multiplying. In the next one, we subtracted when we were dividing. In the third one, we had a power to a power. That's when we multiply the exponents. All right, the fourth and the fifth one are related to each other, or similar to each other, in that if you have something in parentheses, say c times d, both raised to the r power, you would raise each of those to the rth power. Same with number 5, if you have c over d, it's all in parentheses, raised to the r power, that means both c and d are each raised to the rth power. Now on the side here we have that d does not equal 0. That's just to be sure that when we're talking about these laws, in this fraction, c over d, if d is equal to 0, then this is not going to hold true, right? Because then you'll have an undefined fraction. Okay, and then the last one is if you have a negative exponent, c to the negative r, that's equal to 1 over c to the r. So in other words, what you would do is you would take the negative off of the exponent and move that whole thing into the denominator. Okay, and again, c cannot equal 0 here, otherwise you'd end up with 0 in the denominator, giving you an undefined fraction. Now let's go ahead and apply these laws of exponents to some examples. All right, here's the first one. 64 to the 1/3 x squared y cubed times x to the 3rd y to the negative 4th. Okay, so we notice how we are multiplying. We have x squared y cubed times x cubed y to the negative 4th. When we're multiplying and when we have the same base, we can add exponents of the same base together. So the x cubed and the x to the 3rd, because they are the same base, we can add those exponents and get x to the 5th. Same thing with y, we have y to the 3rd, y to the negative 4th. We can add those exponents together and get y to the negative 1st. Now let's deal with the 64 to the 1/3. 64 to the 1/3 we can write as the cube root of 64. And that we can write as, well, the cube root of 64 is equal to 4. So now we have 4x to the 5th, y to the negative 1st. Now in general, we like to, in order to simplify our answers, we like to have our answers with all positive exponents. So this y to the negative 1st, we'll go ahead and use that last law of exponents. Remember, when you have a negative exponent, you take the negative off, and then you move that entire thing into the denominator. So y to the negative 1st, take off the negative, now we just have y to the 1st, and we're going to move y to the 1st into the denominator. So this is going to be 4x to the 5th divided by y. All right, let's look at another example. We have 8r to the 3/4, all in parentheses, raised to the 1/3. Now, because you have a parentheses in there, that should be hopefully a clue that means that that 1/3 exponent that's on the outside of the parentheses applies to each part. So 8 is raised to the 1/3, r to the 3/4 is also raised to the 1/3. Okay. So now let's see if we can simplify this second one here, r to the 3/4 to the 1/3. What we have here is a power to a power. When that happens, that's using the third law of exponents, and that third law tells us if we have a power to a power, we can multiply those exponents. So multiply 3/4 times 1/3. That gives you what? 3/12, which is 1/4. So now we have 8 to the 1/3, r to the 1/4. And then let's see if we can simplify 8 to the 1/3. That's the same as the cube root of 8, which is 2. So 2, r to the 1/4. No negative exponents there. So that is our answer. All right, example 5. X to the 5th, y to the 4th, all in parentheses squared, all over x cubed, y to the 9th. Okay, let's deal with that numerator first. So we have x to the 5th, y to the 4th, all squared, which means that squared applies to both of those. So x to the 5th squared, y to the 4th squared. For each of those, we have a power raised to a power. Now remember, by the third exponent law, that means we are going to go ahead and multiply those exponents. So x to the 5th squared is the same as x to the 10th. Y to the 4th squared is the same as y to the 8th. All right, now we can apply the second exponent law, and we can go ahead and notice that we are dividing. X to the 10th divided by x cubed, y to the 8th divided by y to the 9th. So we can go ahead and subtract, and we get x to the 7th, y to the negative 1st, right? 8 minus 9 is negative 1. And then we have a negative exponent in there. Apply that last exponent law, and that's going to give us y to the 1st in the denominator. So this is x to the 7th divided by y. All right, example 6. We've got some fractions in there, some rational exponents in there. We have x to the 3/5, in parentheses x to the negative 3/5 minus x to the 12/5. So here, let's go ahead and distribute, right? We have x to the 3/5 times x to the negative 3/5 minus x to the 3/5 times x to the 12/5. Now, because for each of these, we have x to the 3/5 times x to the negative 3/5, this applies the first exponent law because you're multiplying with the same base, which means you can go ahead and add the exponents. So x to the 3/5 plus negative 3/5, and then x to the 3/5 plus 12/5. That first one is going to give us x to the 0. Second one is going to give us x to the 15 over 5, or x cubed. So now we have x to the 0 minus x cubed. Now anything to the 0 power is going to equal 1. So this is 1 minus x cubed. Okay, the last thing we're going to talk about today is rationalizing the denominator. So in standard form, we never have a radical in the denominator. Now, the reason for this is that this was actually the preferred form before the use of calculators, and this skill will be very useful in calculus. Okay, so why is this a preferred form? Because normally it's easier to think about dividing by an integer value rather than by a square root of 3, for example. So before the use of calculators, this was the preferred form. It was easier to make calculations with, and so it has become our standard form. So to rationalize the denominator, we multiply by the square root of a over square root of a if we have the square root of a in the denominator. On the other hand, if you have something more complex, if you have a minus square root of b over a minus square root of b, if you have a plus square root of b in the denominator. Now you'll notice that this hopefully looks similar to what we did when we were working with imaginary numbers, and we were talking about how we get rid of I in the denominator. Was a very similar strategy, right? We would use what we call a complex conjugate that we would multiply by. Here we just call it the conjugate because it's not complex. It doesn't involve imaginary numbers. But you're still trying to do the same thing. You're still trying to get rid of that square root in the denominator. And so by multiplying by the conjugate, you're able to get the outer and inner terms. When you multiply those out, will end up canceling each other, which leaves you with some sort of integer value to work with. Okay, so the first one here, 7 over root 5, if you multiply that by root 5 over root 5, we end up with 7 root 5 in the numerator. And then square root 5 times square root of 5 is square root of 25, which is equal to 5. And that's it. That's a rationalized denominator. So with these, the way you double check to see whether or not you're done is just check your denominator. Do you still have a square root in the denominator? If not, you're all set. Here's the second one. We have 3 plus root 6 in the denominator. So here's where the conjugate comes in. You're going to go ahead and multiply by 3 minus root 6, both the top and the bottom. Okay, so let me just write that out here. So this is equal to 6 minus 2 root 6 in the numerator. And in the denominator, you end up with 3 times 3, that's 9. You end up with a minus 3 root 6 and a plus 3 root 6. Those are going to cancel. And then, for the last terms, when you multiply those, root 6 times root 6, that's the square root of 36, which is 6. So you end up with 9 minus 6 in the denominator. 9 minus 6 is 3. And so now, looking at what we no longer have a radical in the denominator, so we have successfully rationalized that denominator.